Analyzing circuits using a brute force application of KVL, KCL, and Ohm's law can be very labor intensive. Using circuit reduction requires less effort but isn't appropriate for all circuits. In this video, I'll introduce nodal analysis, which is a technique to reduce the number of unknowns in just about any circuit. First, I'll quickly review the analysis approaches we've used so far. Our models for individual circuit elements are based on a relationship between voltage and current at the element's terminals, such as Ohm's law. The interactions among elements are governed by Kirchhoff's current law and Kirchhoff's voltage law. Using KVL, KCL, and the voltage-current relations allows us to analyze any circuit. In an attempt to reduce the effort required to analyze a circuit, I introduced circuit reduction techniques, including voltage and current dividers. We're still applying KVL, KCL, and Ohm's law. It's just that we're taking advantage of some shortcuts that certain configurations of elements make possible. However, a circuit requires a certain configuration of elements in order for this approach to work. An example is this circuit. None of the elements in this circuit are in either series or parallel. No node interconnects only two elements, and no loop passes through only two elements. Circuit reduction techniques won't help us analyze this circuit. That means that with the tools we've got so far, we're stuck with the exhaustive approach. This approach requires that we define voltages and currents through every resistor. So this would require us to write 8 equations in 8 unknowns, which is a pretty tedious approach for a circuit that's this simple. There are, however, other analysis approaches that do allow us to reduce the number of unknowns in the circuit. The first of these approaches I'll talk about is nodal analysis. Nodal analysis provides a very rigorous way to reduce the number of unknowns in a circuit. Reducing the number of unknowns reduces the number of equations we have to write and solve. In nodal analysis, the first step is to identify our independent nodes in the circuit. Our unknowns are the voltages at these independent nodes, which are called the node voltages. Then apply KCL at each of the independent nodes and use Ohm's law to write KCL in terms of these node voltages. This will give the same number of equations as unknowns, so you can solve these equations to determine the node voltages. Once you have the node voltages, you can find out anything else about the circuit that you want to determine. In the remainder of this video, I'll talk about identifying independent nodes. Identifying the number of independent nodes is important, since that tells you how many equations you need to write and solve. Independent nodes are separated by unknown voltage differences. Examples are nodes that are separated by circuit elements such as resistors and current sources. The nodes at the terminals of a voltage source are not independent, since a voltage source provides a known voltage difference between its terminals. Let's take a look at this in the context of our example circuit. We know that the nodes on either side of the voltage source are not independent. If you know one of the voltages, you automatically know the voltage on the other side of the source. The voltage source tells us that this voltage is 10 volts higher than this voltage. If we choose this upper node as an unknown, say V sub x, then we know that the voltage down here is V sub x minus 10 volts. The voltage at the lower terminal is 10 volts lower than the voltage at the upper terminal. Alternately, I could choose the lower node as being an unknown, say V sub y. Then the voltage at the upper node will be 10 volts higher than V sub y, or Vy plus 10 volts. The point to remember is that we don't need to define the nodes on either side of a voltage source as both being unknowns. If I choose one as an unknown, the other is dependent on that value. The node voltages we determine will be relative to a reference voltage. Voltages are always a difference between 2 points, and the voltages at the independent nodes are defined as being a voltage relative to the reference. The choice of reference node is completely arbitrary. It can be any node in the circuit. The voltage at the reference node is taken to be 0 volts. These are the possible choices for reference nodes in our circuit. We'll do examples of some of the different choices for reference nodes and the resulting independent nodes next. If we choose this bottom node here as our reference, its voltage becomes defined as 0 volts. The voltage source says that this voltage is 10 volts higher than this voltage, so this becomes a positive 10 volts. We don't know the voltage differences between these nodes and any other node in the circuit, so these become our independent voltages VA and VB. If we define this node as our reference, on the other hand, then this voltage is 10 volts lower than this, or negative 10 volts. These two will still be our independent nodes. If we define this as a reference node, this voltage will be independent, and the voltage on one side or the other of the voltage source will be independent. If I choose this as my other independent node, VB, this node becomes VB minus 10 volts. Finally, I can choose the same reference. This is still independent. If I choose this terminal as my independent voltage, VB, this one becomes VB plus 10 volts. Now I'll give some alternate guidelines about how to determine the number of equations you'll need if you use nodal analysis. Independent nodes are separated by circuit elements other than voltage sources. The nodes at the terminals of a voltage source are not independent from one another. If you aren't sure about the number of independent nodes in the circuit, you can replace voltage sources with short circuits and count the remaining nodes. For this example, we'll replace this voltage source with a short circuit. This process is called killing the source. Now the nodes on either side of the voltage source are combined into a single node. For this example, I end up with nodes here, here, and here. One of these will be a reference node, which means the circuit has two independent nodes. So if killing the sources results in n nodes, you end up with n minus 1 independent nodes, since one of these nodes will become your reference node. Therefore, you need to write n minus 1 equations governing the circuit. I'll provide more information about actually writing the equations in a later video. The process of shorting or killing the voltage source can also be used to identify what are called supernodes. In this circuit, we could define 4 different nodes. However, the nodes on either side of the voltage source are not independent. The underlying idea in nodal analysis is that we identify independent variables as the voltages at the independent nodes, and then write KCL at each of the independent nodes. Since the two voltages on either side of a voltage source are not independent, these two nodes share a single unknown, and we should only write KCL once. The easiest way to deal with this is to put the voltage source inside what is called a supernode and do KCL on all of the currents entering or leaving that supernode. For this example, there are only 3 possible independent nodes now, here, here, and here. Since one of these nodes will be a reference node, we have 2 node voltages we need to determine, and we only write KCL twice. That's the basic idea behind defining the minimum number of node voltages for a nodal analysis. In the next video, I'll talk about writing the equations that govern those voltages. And then we'll use the node voltages to determine any voltage or current that we actually need to know in the circuit.